Assalamualaikum warahmatullahi wabarakatuh and good day to all students. Today you are going to learn about Fourier series. Okay, what is Fourier series? Fourier series is a series that represents a real periodic function as an expansion in a series of sine and cosine. I've shown you here few examples of periodic functions. So we have a square wave function, sawtooth wave function, triangle wave function, and semicircle function. So you can see that some of the periodic function have discontinuity at discontinuity points. Okay, but some of the periodic functions, they are continuous. So how can you write down a series that represents, okay, the function, okay, for example the square wave function, as an expansion in a series of sine and cosine? Okay, I repeat, how can you write down a series that represent the real periodic function as an expansion? Okay, this is an example of the Fourier series as an expansion in a series of sine and cosine. So why sine and cosine? This is because these two trigonometric functions are periodic function that is naturally harmonically sinusoid, and they are continuous function. So how can we represent this function as a beautiful function? Okay, by writing this a series that contains a sine and cosine function. Okay, so we can see that sine and cosine wave can make other function, right? Why do you need to learn Fourier series? So you can see that in electrical engineering problem, some of the function, okay, some of the input function, okay, they are periodic functions. So we can see the applications in vibrating analysis, in optics, in signal processing, in image processing. Okay, then it will be very useful if you can write down or you can determine a series that can represent the real periodic function. Okay, and another application is this method can be used to determine the unknown coefficients arise in solving PDE. So we are going to revisit the Fourier series in the partial differential equation chapter. Okay, so let's take a look at the definition of Fourier series. Let ft be a periodic function defined in the interval negative L to L with period t equals to 2L. What is t? The fundamental period. If the function ft is either continuous or has finite discontinuities at some points, we have discussed about this in previous slide, in the interval negative L to L, therefore the Fourier series for ft is given by, so this is the formula of Fourier series. So ft, the function, the periodic function ft, is equals to a naught on 2 plus the summation of an cos n pi t on L plus bn sin n pi t on L. So this is what does it mean by representing the function as an expansion of series of cosine and sine function. So let's recall what is periodic function. Okay, let's revisit the example in periodic function. So we were plotting the function ft equals to t before. Okay, so we have t equals to -1 to 1. Alright, so ft equals to t is between -1 to 1 and it's periodic function that has fundamental period 2. Okay, which means that every time it increases or decreases by 2 units, then it will repeat the same plot. Okay, so the plot gonna look like this. Okay, so see, this is -1 and this is 1. Okay, this is t, this is ft. Okay, so we're going to plot this from -1 to 1, and this is the plot of one complete cycle from -L to L. Alright, so which means that the period the interval of from minus L to L, okay, is actually the sketch of one complete cycle. Okay, so this is from negative L to L. Okay, and based on the sketch, L is equals to 1 and T is equals to 2L, so this is equals to 2. So this is how you determine the value of L. Okay, let's go back to the formula. Alright, so we have the formula of Fourier series formula here, how to write down the periodic function as an expansion of sine and cosine. Okay, and we can see that we have three unknown Fourier coefficients, a0, an, and bn. Okay, so this is the formula of how can you calculate a0, an, and bn. So a0 formula is equal to 1 on L. Okay, the integration of ft with respect to t from negative L to L. Okay, then we know that L, okay, if you have this periodic function, L is equals to 1. Alright, then the function here from t minus 1 to 1, the function ft is equals to t. Alright, then going to solve the integration, substitute the limits. Alright, then we're gonna get what is the Fourier coefficient of a0. Okay, so this is formula of an equals to the ft times cos n pi t on L. Alright, okay, we're going to substitute L is 1 minus 1 to 1 over 1, and the function ft is equal to t. Alright, so in order to solve the an, so we have to use tabular methods. Right, so bn equals to 1 on L, the integration of ft sin n pi t on L with respect to t from negative L to L. So you can see that an is the multiplication with cos n pi t and L. So therefore, in order to solve an, also is a multiplication of ft by the cos n pi t on L. Okay, same goes to the bn. So these are the formulas of how can you write down the Fourier series, and as well how can you determine the Fourier series coefficient. Okay, how about the Fourier odd and even series? Okay, I can noted that all functions, okay, can be calculated, okay, the series using the Fourier series formula that we have discussed in the previous slide. Okay, however, we can reduce the difficulty, okay, or the technical calculation of finding the Fourier coefficients a0, an, and bn if we know the type of the function. Okay, if the function is odd function, the function is an odd function, then we're going to use Fourier sine series formula. Why Fourier sine series? This is because sine function is an odd function. Okay, if the function is an even function, we're going to use Fourier cosine series. If the function is neither odd nor even function, then we're going to use the original Fourier series that we have discussed in the previous slide. Alright. Okay, if the function is an odd function, use Fourier sine series. Some books call Fourier odd series. So if the function is odd function, then the Fourier series is given as ft equals to the summation of bn sin n pi t on L, and from 1 to infinity. So you can see that there are no coefficient of a0 and b0 as a0 and an. Okay, this is due to that a0 equals to 0 and an equals to 0. So you don't have to struggle or to burden yourself to calculate what is the value of a0 and an. Okay, since if the function is odd function, a0 equal to 0 and an equals to 0. Okay, and the formula of bn is given as, okay, the integration. Okay, so you can see that since odd function and even function have symmetric properties, so we're going to solve the function, the integration in half range from 0 to L instead of full range from negative L to L. Okay, then multiply by 2. Okay, so the formula of bn is ft equal to sin n pi t on L. with respect to t from 0 to L, then multiplied by 2 on L. Okay, so you're going to reduce some difficulties, okay, reduce the complexity of the calculations. All right, this is when you have odd function. So when you have an even function, when the function is an even function, then we're going to use Fourier even series or Fourier cosine series. So these are the formula. Ft equals to a naught on 2 plus the summation of an cos n pi t on L, n equals to 1 to infinity. Where is Bn? There is no term of Bn due to that Bn equals to 0. And the formula of A naught and An are given here. Alright, again, due to the symmetric properties, so we only need to solve the integration in half range 0 to L, then multiplied by 2. Okay, and this is formula of An. So note that if the function is neither an odd or an even function, please, you have to use the Fourier series, original Fourier series formula. Okay, working steps of Fourier series or Fourier sine and cosine series. Step 1, okay, this is very important step. You have to sketch the function and determine the type of function, whether the function is an odd function or an even function or neither function. Alright. Step 2, we're going to determine the parameter L. So we know that the parameter L can be determined by plotting from the sketching, okay, from negative L to L. Okay, step 3, calculate the Fourier coefficients A naught, An, Bn using formula. Step 4, we're going to substitute the Fourier coefficients A naught, An, Bn into the Fourier series formula or into the Fourier sine or into the Fourier cosine formula. Okay, here I list down some helpful identities in calculating the Fourier coefficients. Okay, sine 0 is equal to 0. Okay, I think you knew that already. Cos 0 equals to 1. Right? Sine minus t equals to minus sine t. This is due to the sine function is an odd function. Cos minus t equals to cos t because cosine function is an even function. Sin n pi equal to 0. Bear in mind that n is an integer. Alright, n equals to 1, 2, 3, 4, 5, 6, 7, and etc. So sin n pi, sin pi is 0, sin 2 pi is 0, sin 3 pi is 0. Then we can conclude that sin n pi is equal to 0. Cos n pi equals to minus 1 to the power of n. Okay, cos pi is minus 1, cos 2 pi is 1, cos 3 pi is minus 1, cos 4 pi is 1, okay, and etc. So we can conclude that cos n pi is a repetitive of minus 1 to the power of n. Sin 2n pi always equal to 0. If sin n pi equal to 0, then obviously sin 2n pi is also equal to 0. Cos 2n pi equals to 1 because the angle is an even function, an even number. 2n is even number, so cos even number time pi is always equals to 1. For n integers, n equals to 1, 2, 3, 4, 5, 6, and etc. Okay, I'm going to stop here. Alright, we are going to discuss few examples in the next video. Okay, thank you for watching.